In this lesson, we'll discuss pressure loss and head loss in pipe flow. Here we have two pipes filled with a fluid flowing left to right. The inlet of each pipe is denoted by the letter I, while the outlet is denoted by the letter O. In the left scenario, a fluid completely fills the pipe and the pipe is sealed off from the atmosphere. Examples of pipes that are completely filled with fluid are household water pipes, crude oil pipelines, and compressed air lines. In the right scenario, a liquid partially fills the pipe and there is some atmospheric air above the liquid. Examples of pipes that are open to the atmosphere are storm drains and sewer lines. Note that only a liquid can be transported in this manner, as a gas would expand to fill the entire pipe. We will refer to the left scenario as pipe flow and the right scenario as open channel flow. In pipe flow, the pressure at the inlet is usually greater than the pressure at the outlet. This pressure gradient provides the main driving force for transporting the fluid through the pipe system if the flow is horizontal or uphill. If the flow is downhill, both the pressure gradient and gravity may be important. For open channel flows, the pressure is approximately constant along the entire surface of the liquid, and gravity is the main driving force transporting the liquid along the pipe system. Since there is no pressure gradient, the liquid can only flow downhill. We will now examine why pressure gradients develop in pipe flow. Here we have two different pipes of radius r. Both pipes are tilted upward at an angle phi. The fluid in the first pipe is fully developed and turbulent, while the fluid in the second pipe is fully developed and laminar. Next, we zoom in to examine a small fluid cylinder that is centered in the middle of either flow. The cylinder has a length L and a radius lowercase r. There are three external forces acting on the cylinder in the axial direction. First, a shear stress tau acts at the sides of the cylinder due to velocity gradients in the flow. The force due to the shear stress is equal to tau times the area of the cylinder wall, 2 pi r L, and opposes the flow. The resultant force vector is drawn at the top portion of the cylinder for convenience, but the force is actually applied over the entire cylinder wall. Next, the weight mg acts at the center of the cylinder and points downward. The component in the axial direction is mg times sine phi. Finally, a pressure force acts at the two ends of the cylinder. On the upstream side, the pressure force is pressure P times the area pi r squared. On the downstream side, the pressure is changed by a small amount delta P, and the resulting force is P minus delta P times area pi r squared. Newton's second law in the axial direction states that the sum of external forces acting on the cylinder in the axial direction is equal to the cylinder mass m times the acceleration in the axial direction ax. Since we have fully developed flow, the cylinder's velocity does not change in time and ax is 0. The sum of the forces becomes p times pi r squared minus the quantity p minus delta p times pi r squared minus tau 2 pi r L minus mg sine phi. Solving for delta p, we see that the pressure drop is related to the shear stress and orientation angle. This equation is valid for both fully developed laminar and fully developed turbulent flows. It shows that the pressure will decline along a pipe if the force due to shear stresses, which are often called viscous effects, are greater than the component of the weight in the axial direction. For a horizontal pipe, in which phi is equal to 0, a pressure drop will always exist. A pressure drop also will exist if the flow is uphill, since sine phi would be a positive number. It will be shown in a future video that the shear stress is proportional to velocity gradients. So this equation indicates that viscous stresses, resulting from the presence of velocity gradients, reduce the mechanical energy of a flow in the form of reducing pressure. The mechanical energy is converted into thermal energy, which does not serve a useful purpose in most fluid mechanics applications. Next, we will examine how pressure changes qualitatively in a pipe system. Here we have flow entering a horizontal pipe from a reservoir. There's an entrance region where the flow is developing and the velocity profile changes in the axial direction. Then the flow becomes fully developed and the velocity profile is constant in the axial direction. Once a flow becomes fully developed, pressure declines linearly in the axial direction. However, in the entrance region, the pressure gradient is greater due to two factors. First, in order to maintain conservation of mass along the pipe, the core region accelerates as flow in the boundary layer near the wall is decelerated. The energy required to accelerate the core region comes from the potential energy stored as pressure. Second, if the flow is required to change sharply at the entrance, flow separation can occur. This will increase the shear stress in the flow, and a greater pressure drop is required to balance out the enhanced viscous effects. The loss of pressure in a pipe system is due to frictional losses, which are quantified by the head loss term in the conservation of energy equation. Here we have a section of straight pipe of length L and diameter d, with the pipe oriented at an angle phi. We draw a control volume around the pipe section and apply the conservation of energy equation. We will label the inlet as 1 and the outlet as 2. The velocity at the inlet and outlet are the same, so the v squared over 2g terms cancel out. Additionally, the pump head and turbine head terms are 0 because there are no pumps or turbines in the control volume. We now have the pressure head plus elevation head at the outlet equals the pressure head plus the elevation head at the inlet minus the head loss. The change in elevation is equal to L sine phi, and we label the change in pressure as delta P. Substituting these expressions into the conservation of energy equation gives us delta P over gamma minus L sine phi equals the head loss. We move the equation to the top of the screen and continue. Earlier we found an expression for Newton's second law for a fluid cylinder in a pipe. Now we will apply this equation for a fluid cylinder consisting of all the fluid in the pipe, which is the same system we considered when applying the conservation of energy equation. The radius lowercase r is half the diameter, and the shear stress tau is the shear stress at the wall, which will be denoted as tau w. Newton's second law becomes delta P equals tau w pi dl plus mg sine phi divided by pi d squared over 4. The weight of the fluid in the pipe can be rewritten as gamma times the volume. The volume of the pipe is L times the area, pi d squared over 4. Plugging in the expression for mg and rearranging the equation, we obtain delta P over gamma minus L sine phi equals 4 tau wl over gamma d. Comparing the conservation of energy equation with Newton's second law, we now have an expression for the head loss. HL equals 4 tau w over gamma times L over d. We can develop a more useful form of the equation by multiplying the numerator and denominator by 2g rho v squared. Rearranging the variables, we have 8 tau w over rho v squared times L over d times v squared over 2g. We will define the first term, 8 tau w over rho v squared, as the friction factor F. We now have the Darcy-Weisbach equation, which will allow us to calculate the head loss for straight pipes for both laminar and turbulent flows. In a future video, we will discuss how to obtain F, which is often called the Darcy friction factor.